Here we have the alternating series, the negative 1 to the n times the square root of n dividing by n plus 2. And we want to show that this alternating series converges. And so first we have to show that the limit of a sub n is equal to 0, and then we have to show that a sub n is greater than or equal to a sub n plus 1. And so first, notice that this is the same as this. And so we have a sub n is equal to this part. And so the first we need to show that the limit of a sub n is equal to 0. And to find the limit here, we can divide the top and the bottom by n. Now for the bottom n divided by n, it's just 1, and then plus 2 over n. And then the top right here, we have the square root of n dividing by n. And then let's go ahead and work that out. So we have this right here. This is the same as this, n to the 1/2 dividing by n to the first. And recall that when you divide, you subtract the exponents. So 1/2 minus 1 will be negative 1/2, which is the same as 1 divided by n to the 1/2, which is the same as 1 divided by the square root of n. So the top we get 1 dividing by the square root of n. So as n approaches infinity, 1 dividing by the square root of n will go to 0, and in the bottom we get 1 plus 0, which is 1. So we get 0. So we have shown condition number 1, the limit of a sub n is equal to 0. And now we need to show that a sub n is greater than a sub n plus 1. So this is a sub n, and then a sub n plus 1, then in the place of n just put plus 1, n plus 1. And so this becomes the square root of n plus 1 dividing by n plus 3. And now we can see that this is going to be hard to compare a sub n with the a sub n plus 1 here, because we have the denominators, they're different, and then the denominators are different, and then the numerators are different also. And so it's going to be difficult to compare these directly. And so one way to get around this right here, if we form the corresponding continuous function of the square root of x dividing by x plus 2. And then for the series starts at 1 to infinity. And so to show that this is a decreasing sequence, to show that the sequence is getting smaller and smaller and smaller. And then we have to show that the derivative here is negative on the interval from 1 to infinity, or some finite number to infinity. And so let's take the derivative here. So we have f prime of x, and this is the quotient. And so to get the derivative of this one, we can go ahead and rewrite this as the x to the 1/2, and then the derivative, the quotient, would be the bottom, x plus 2 on the denominator, times the derivative, the top. So the derivative of x to the 1/2, so we need the derivative of x to the 1/2, and then minus x to the 1/2, and then times the derivative of the denominator, and then dividing by the denominator squared. So once again, to show that a sub n, the sequence a sub n is decreasing, one way we can show that is that show the corresponding continuous function is negative on the interval of 1 to infinity, or some finite number to infinity is negative on that interval. So we get x plus 2, and then the derivative here will be 1/2 times x to the negative 1, negative 1/2, because we're subtracting 1 from the exponent. And then minus x. Remember that x starts at positive number 1 and on to infinity. So x is always it's going to be positive. And then we have the bottom here. And so here x starts at 1, and so the bottom is always going to be positive. And then times 1, just times 1. And then right here, x times 1/2, this is the same as x to the first. So it's x to the first times 1/2, x to the negative 1. So x to the first times 1/2, x to the negative 1, that would be 1/2 x to the 1/2. Remember that when we multiply, we add the exponents. So 1 plus negative 1/2 is 1/2. And then plus x two times 1/2, x to the negative 1 will be just 1 x to the 1/2 to the negative 1/2. And then we have the minus x to the 1/2. And then here we have 1/2 x to the 1/2, and then this is 1 right here. So this is x to the 1/2, and this is x to the 1/2. So we can combine these two right here. So a half minus 1 will be negative 1/2. Again, this is 1/2. This is minus 1. 1/2 minus 1 is minus 1/2. So this is the derivative right here. And if we graph this derivative, this is what it looks like. And if we graph this derivative function right here, this is what the graph looks like. And so we zoom in a little bit. And so we interested in the x from 1 to infinity. So at 1, we see that the derivative is positive. And then beginning at 2, that's when the graph is below the x-axis. So that's when the derivative is negative. And so we can see that the derivative is negative beginning at 2. And so this derivative function right here is negative for x greater than 2. And so what this means is this: remember that the function f of x is the function that corresponds to the sequence, the square root of n divided by n plus 2. And so since the function, we have just shown that the derivative function is negative for x greater than 2. And so what that means is that the function, this function right here, the square root of x divided by x plus 2, is decreasing beginning at x equal to 2. And therefore, so let's write it down. So the function f of x equal to the square root of x divided by x plus 2. Is decreasing for x greater than 2. And so the corresponding sequence is also decreasing for n greater than 2. And therefore we have shown that the a sub n for n greater than 2. And again, when we do this type of comparison, as long as this is true, beginning for some finite n could be starting at 1, at 2, at 3, at 4, at 5, some finite number, then this is good. And so now that we have shown both conditions, we have shown that the limit of a sub n is equal to 0, and we have shown that a sub n is greater than or equal to a sub n plus 1. And so by the alternating series test, the original series, this series right here converges. And so that's what we have to do sometimes. We cannot do a direct comparison of a sub n and a sub n plus 1. And then one way to get around it is form the corresponding continuous function and then find the derivative and show that the derivative is negative for x, beginning with some finite number. And then we will have shown that we will have met this condition. And then that will lead to the alternating series converges.